All right, now before I get to some examples, I do want to highlight some of the finer points of the Diels-Alder reaction. And this deals with stereochemistry. And there's a lot of stereochemical aspects that we have to take into account because we're dealing with pi bonds. And so the first thing I want to look at is the stereochemistry of the dienophile. Now, if the dienophile starts off as cis or trans, then that stereochemistry needs to be maintained in the product. And here's what I mean by that. Let's look at this reaction. And I'm just going to label these here 1, 2, 3, and 4, 5, and 6. So I know in this product, I'm going to get a cyclohexene ring. I'm going to number it like this 1, 2, 3, 4, 5, and 6. There's a methyl group on 2, so I'll keep that there. And I want you to look at carbons 5 and 6 of the dienophile. Notice how those cyano groups are going in opposite directions. So they need to maintain that stereochemistry in the product. So I'm going to draw one of those up and one of those down. Now, why did I choose them in that stereochemistry? Well, that's, what I just chose, but it is equally possible to get this one down and this one up. And if it's a 50-50 mixture, what do we call this? This is a racemic mixture. Okay, so now if those cyano groups have been cis to each other, I would have made sure they maintain that stereochemistry in the product. Now, what's a little more complicated is what if there's groups on the 1 and 4 position of the diene? So here's my diene, and I put a couple methyl groups on there, one on the 1 and one on the 4. And I'm going to react it with just this simple dienophile. There's 5 and 6. And I'm going to draw my cyclohexene template. Now, because those methyl groups on the diene started off in a certain orientation, they're going to be going in a certain direction in relationship to each other in the product. And here's how you figure this out. Draw in the corresponding hydrogens here. And what I want you to do is label these from top to bottom, A, B, C, and D. Always label them like that from top to bottom. Because here's the relationship. It doesn't matter what the groups are. A and D will always be cis to each other in the product. And B and C will always be cis to each other in the product. And so when we draw group A and group D, I'm going to draw them either both up. Oops. That would just be a methyl group like this. And then for emphasis, I'll draw the hydrogens there. Now, what if this diene, I'll use the same diene, but just have one of those methyl groups in this position. So again, I'll start with my cyclohexene template. And I'll label these again, A, B, C, and D. Keeping with this theme, A and D should be cis to each other. That means this methyl group and this hydrogen are cis, and then this hydrogen and this methyl group are cis. Now let's examine both the products. Should I draw the enantiomer for the first reaction here, for this guy? Well, this turns out to be a meso compound. Same groups on both sides of that midline going in the same direction. This, however, is not a meso compound, so I will draw its enantiomer. So do we still have to worry about this stereochemistry stuff? Absolutely. You cannot forget it. You won't be able to even forget it next semester either. Now, there's an interesting kind of case that happens when we're dealing with dienes that are part of a ring. Here's what I mean by this. Here's a conjugated diene. It's just that the ends of it are connected together in a ring. And I'm going to react it with this dienophile. Now let's just get the logistics of this down first before anything else. Let's label our diene there, 1, 2, 3, 4. And then I'm going to label my dienophile 5 and 6. And just for good measure, let's label that last carbon of that 5-membered ring as 7. And what I want you to do is kind of forget 7 for right now. And I'm going to draw my cyclohexene template. I'm going to draw it a little bit different though. I'm going to draw it like this. Right, here's still 1, 2, 3, 4, 5, and 6. And there's my cyclohexene ring. Now, when I draw the mechanism for this, I want you to pay close attention to the arrows. Did I break any bonds around number 7? No, number 7 is still connected to 1 and 4. So the way I'm going to represent that is with this kind of bridge here that goes upwards. There is carbon number 7. So when the conjugated diene is part of a ring, you're going to get these bridges. It forms what's called a bicyclic product. Now let's draw what will happen with the dienophile, because I got a substituent on number 5. Either that carbonyl can be going this way, and they call this the endo product, or it could be going this way. This is called the exo product. Now, if there are substituents like this carbonyl group, endo is the favored product because it puts that substituent farther away from this bridge. So here, there might be a little bit of interaction between that substituent and that carbon that's forming the bridge there. I'm going to kind of go, I'll come back to this page in 1 minute. And here's more of kind of a sort of three-dimensional way to look at endo versus exo. So look at how far away that substituent is to the bridge there. Now imagine it if it had been attached to, say, the exo part here. It would be a lot closer to that bridge. So if there is a substituent on the dienophile, and you're forming a bicyclic product like this, the endo is the favored product. Okay, let's look at another example of this. This time I'm going to use a diene that's involved in a six-membered ring. And I'm going to kind of use like a sort of bulky dienophile to, again, illustrate this endo versus exo. So let's draw in our six carbons that are involved in the Diels-Alder. And then I'm just going to call this 7 and 8. And I'm going to start off because the diene is part of a ring. I'm going to still draw cyclohexene. I'm just going to make it look a little weird like this. So there's my cyclohexene. 1, 2, 3, 4, 5, and 6. And notice I still have carbons 7 and 8 to deal with. Well, 7 is still attached to 4. So there's 7. And it's also still attached to 8. And 8 is also still attached to 1. So we have this 2-carbon bridge there. So 7, 8 are right there. Now the dienophile is kind of weird because the dienophile is also in a ring. So how do I demonstrate this being exo? Well, I'm going to do that by, first, let's just draw in the rest of the stuff here. And then I'm going to draw the corresponding hydrogens here going upwards. And that basically means if those hydrogens are up, then this ring is kind of flipped downwards away from the bridge. All right, so with that in mind, I'm going to go back a few pages to our examples. And let's put this all into kind of perspective. Let's summarize it all. So let's start with this. And again, I'm just going to start with my template here. Start here in numbering 1 through 4, and then number the dienophile 5 and 6. And I could use a normal cyclohexene ring here because the diene is not part of a ring. And I'm just going to number these 1, 2, 3, oops, 3, 4, 5, and 6. And let's practice drawing a mechanism too. So again, everybody loves these because it's one step, just 3 arrows. You can start at any pi bond there, it doesn't matter. Okay. Now let's deal with stereochemistry here because we have groups both on the diene and the dienophile. Do I care about the dienophile? Is that a cis or trans double bond? No. So I don't have to worry about stereochemistry there because it's not forming a chiral carbon. But notice how in the diene, there are groups on 1 and 4. So that means I have to put them in a particular position. And I'm just going to erase these real quick. If I draw on the corresponding hydrogens and then use my letters A, B, C, and D, groups A and D should end up cis to each other. Now, you don't have to draw the hydrogens in if you don't want to, but B and C are cis to each other because they're assumed to have the dashed wedge. And it's equally as likely that those OCH3 groups were going downwards. So that's why we would get a racemic mixture. All right, let's look at another example here. All right, now there's a couple weird things about this. First of all, our diene is in a ring. So let's start off with our template there. And I'm just going to call this number 7. The other weird thing is that our dienophile is a triple bond. That's okay. It's a pi bond. And I really want to emphasize the mechanism here with this because I'm going to use one pi bond to do that. So if I take away one pi bond from that triple bond, how many pi bonds are left between carbons 5 and 6? So shout that out to your computer. Now, since the um, diene is in a ring, I'm going to use this weird looking cyclohexene template. And again, here's 1, 2, 3, and 4. And there's 5 and 6. And I'm going to put number 7 as a 1 carbon bridge right there. Now, 5 and 6 started out as a triple bond. It gave up one pi bond in this. So it still has one pi bond left. Now, because there aren't any other groups on that triple bond, they're just hydrogens, I don't have to worry about endo versus exo because there isn't any endo or exo. All right, and let's do one more. This time we'll have the diene be part of a 6-membered ring. And we have a cis dienophile. So let's start with our template again. 1, 2, 3, 4, 5, and 6. And I'm going to call this one 7 and 8. And since our diene is part of a ring, I'm going to use this weird looking cyclohexene template. So 1, 2, 3, 4, 5, and 6. And now let's deal with carbons 7 and 8. Well, since it's a 6-membered ring, I'm going to have a 2-carbon bridge here going upwards. So there's 7 and there's 8. Now let's deal with carbons 5 and 6 because there's a couple groups on there. Notice that this is a cis dienophile. And I want to draw them, since there's substituents there, to emphasize the endo product if possible. So I'm going to put one of those CO2H's down here, like this. And that means the other CO2 group has to go here, like that. Now, what if they had been trans? So if they had been trans, then I can put one of those CO2H groups in the endo position, but I can't put the other one endo. It has to go exo. So sometimes you're forced by stereochemistry to not necessarily follow that endo versus exo thing.